Welcome to this fourth video about linear regression, where we'll discuss the so-called R-squared value. In this lecture, we'll look at the coefficient of determination, which is denoted as R-squared. The R-squared value tells us the proportional variance of the response variable that is explained by the explanatory variables in a regression model. In a previous video about the basics of linear regression, we fitted the line to data on systolic blood pressure and age from 7 individuals. In this video, we'll use the same example but with new data to estimate the so-called R-squared value. In this example, the R-squared value will tell us the proportional variance in systolic blood pressure that can be explained by the age. By using a software, the optimal value for the intercept was computed to 109.86, whereas the optimal value for the slope was computed to 0.36. The following equation therefore represents a line that fits best to the data, which results in the lowest sum of squared residuals. To calculate the R-squared value, we first need to calculate the sum of squared residuals for our model, which is the sum of the squared distances between the regression line and the data points. These calculations are the same as we discussed in the video about the least square method. To calculate the distances between the data points and a line, we first need to know the values of the line for the corresponding x values of the observed data points. This can be calculated by our equation, where we insert the x values, the ages, for each of the 7 observations in the equation. For a more detailed explanation, watch the video about the least square method. The following rounded estimated values were calculated based on the equation for each observation. For example, according to the line, a person who is 33 years old is estimated to have a systolic blood pressure of 121.9. Next, we calculate the square distances between the line and the data points. For example, the difference between the systolic blood pressure 130 obtained from person number 4 and the estimated value 125.9 is 4.1. Remember that the distance between a data point and a line is called an error or a residual. The square of 4.1 is about 17.0. The square distance between this data point and the line is therefore about 17. Next, we sum all these squared errors so that we get the sum of squared errors, SSE. We see that the sum of the squared errors is about 146.5. Next, we calculate the total variance of the response variable, which is based on a horizontal line with a slope of 0. The y value of this horizontal line corresponds to the mean of the response variable. This is the same as just plotting the y values without considering the age, and then calculate the mean of the systolic blood pressure. The mean systolic blood pressure of the 7 individuals is 126.1. The estimated values according to the horizontal line are therefore simply the mean of the observed systolic blood pressure values, which is equal to 126.1. The estimated values according to the horizontal line are therefore 126.1. If you subtract the estimated values from the observed blood pressure values and square those differences, we get the following values. If you sum all those square differences, we get the value of SST, the total sum of squares. In this case, the total variation is 346.9. Once we have worked out the SST and SSE values, we can use the following equation to calculate the R-squared value. If we plug in the values and do the math, we see that the calculated R-squared value is 0.58, which means that 58% of the variation in the systolic blood pressure between the different individuals can be explained by the difference in their age. Note that we here estimate the R-squared value on only 7 observations. To get a more accurate prediction of the R-squared value, we need a much bigger dataset. In summary, the R-squared value tells us that 58% of the variation in systolic blood pressure that we see among the individuals can be explained by their age. We see that the variation around the mean is greater compared to the variation around the regression line. SST is the total variation around the mean, whereas SSE is the variation around the line. SSE is therefore the variation that cannot be explained by the model. The numerator therefore represents how much variation that is explained by the model. When we divide by SST, then we get the proportion of variation that is explained by the model. The R-squared value can also be expressed as 1 minus SSE divided by SST. Note that SSE divided by SST gives us the proportion of the total variation in the systolic blood pressure that is unexplained by the model. In our example, this corresponds to 42%. And when we take 1 minus of what is unexplained by the model, we get the proportion of the variation that is explained by the model. There are therefore a lot of other things that might affect the blood pressure rather than just the age. For example, a model including also the explanatory variables body mass index and gender might give a much better prediction of the blood pressure. Suppose that the difference in blood pressure could be completely described by the variable age. Then all the data points would fit on the regression line like this. This would mean that all people of the same age would have exactly the same blood pressure. The only thing that can change the blood pressure is aging. In such a scenario, there will be no variation around the line, and the value of SSE would therefore be equal to 0. The R-squared value would then be equal to 1, since the age completely describes the variation in the systolic blood pressure between the individuals. In comparison, if the systolic blood pressure did not change at all during aging, we would expect that the data would scatter around a horizontal line like this. The values of SST and SSE are then expected to be the same, and the numerator would therefore be equal to 0. The R-squared value is therefore expected to be 0 if the explanatory variables cannot explain the data. In a linear regression model where we estimate both the intercept and the slope, the model cannot predict worse than the horizontal line, which means that the R-squared value is a value that ranges between 0 and 1. Note that the R-squared value is equal to the square of the Pearson correlation coefficient in correlation analysis. For example, the Pearson correlation coefficient for our previous blood pressure data is 0.76. The square of the correlation coefficient is 0.58, which is identical to our previously calculated R-squared value. This was the end of this lecture about the R-squared value. Thanks for watching.